So in the last lecture we discussed about normalization condition, and I would like to state something quite interesting. Do you remember how the wave function of a free particle is represented? Let us try to make the wave function. So a free particle has a unique momentum. Agreed? So what is the price that we pay for a unique momentum? Remember Heisenberg uncertainty principle, that any uncertainty in momentum multiplied with uncertainty in position has to be greater than equals to h cross by 2. Now the uncertainty in position is greater than equals to, so this is just a number, h cross by 2 is just a number. Look at here, this is the uncertainty in momentum. The uncertainty in momentum for a free particle is 0, because for a free particle we exactly know that what is the momentum, as a result of which the price that we pay is that the uncertainty in position blows up. Agreed? The uncertainty in position blows up. This is problem number 1. Okay. Problem number 2. How do you define the wave function of a free particle? Well, we can define the wave function of a free particle as this: some normalization constant a that we need to find, and we can just write e to the power say minus I, okay, p by h cross x, okay, and there will be a time part f of t, and that time part will be nothing but the exponential in energy. As I already told you, the time part is somewhat like this: e to the power minus I e by h cross into t. But here we are not concerned with the time part, we are concerned with the space part. So my work is now to normalize the wave function. So consider the space part. So what is the space part? The space part is just this. Okay. So this is my space part. Now question is, I want to normalize. So let us see what happens when I try normalizing. And why do I want to normalize? I want to find the value of normalization constant a. So let us see what is the normalization condition. It says that you go from minus infinity to infinity. You have psi star, psi we have already discussed in our last lecture, into dx. It should be 1. This is my normalization condition. Now let us try to evaluate this. So what happens? So I get a minus infinity to infinity. So what is psi star? As I told earlier, that psi star will be the conjugate of psi. So it will, so minus I will convert into plus I. So I p by h cross x. And what is the other one? Other one will be a e to the power minus I p by h cross x. So that has to be 1. So what do I get? I get, so there is the dx here. Okay. So what do I get? I get an a square, and I get integration minus infinity to infinity dx equals to 1, because the e to the power ikx, ipx and minus ipa, they get cancelled. Now unfortunately I cannot calculate the normalization constant a for the free particle. This is the most unfortunate thing for the wave function of a free particle, that the normalization is not good. Now we have two options: whether we betray the entire theory, we say that hey look, the entire theory is bad, these things are in some places these are not working, so we need to betray the quantum mechanical theory that we have invented just right now in this lecture series, or we can do some trick of hand. Now when a theory is correct in many places, then it is better we don't betray the theory. So that what happened for quantum mechanics, it was nearly correct for many places, but it is somehow creating problem with the normalization of free particle. So it's better we use a slight trick of hand and define the normalization of free particle. Although we know that normalization of free particle is a problematic thing, but we cannot give up the theory, okay, because it's correct. So all we can do is we can use a slight trick of hand. So that trick of hand is provided by the delta function. So in the next lecture, we'll talk about the delta function and we'll solve the problem of normalization of the wave function of a free particle.